Well, throughout history, we've used metaphors based on the most advanced technologies that we ourselves have happened to build as a theory or a proto-theory for how the brain might work. So it's not surprising then that plumbing and aqueducts were for a time a going theory. Telephone switchboards, digital computers, supercomputers, the internet, the cloud. What's next? Well, some wag might say Facebook.
I hope not.
Give me a break. I told that joke 2 years ago, literally, in a talk like this, and this appeared in the science press within 2 weeks after that. There are people who have actually claimed that patterns of activity in mammalian neocortex have some properties that made them think of Facebook. Really? Come on. It's easy to fall into the trap of thinking that this is how the brain works. That the eyes are pelting the brain with information about what's going on outside of us. And of course, there's a little person sitting there looking at what the eyes are providing the brain. And that's perfectly reasonable, right? Well, no. Because it gets you into this kind of fallacy. Well, how does that little person work? Well, it has another little person inside it, which has another little person inside it, which has another little person inside it. This is what our colleague philosopher Dan Dennett calls the homuncular fallacy, that there are little homunculi all the way down, and that's obviously not how it can possibly work. So, sorry?
It's all fractals.
You may have read and heard about two major brain projects, one in the US, one in the European Union, both of which are controversial, both of which are large projects involving large numbers of investigators, lots of money. The only difference between them is the Europeans have actually put real money against the project. The US has yet to do that, and it is unclear whether it will put new money against the project or not. Both projects are controversial along the dimensions of big science versus little science. There is a strong feeling amongst the US scientific community, particularly in biology, that large-scale science of the kind that is done by the Large Hadron Collider at CERN, for example, may be necessary for very specialized problems, but that small-scale science done by individual investigators has been extremely powerful in US scientific history. So there's this big science, little science divide. Just a few weeks ago, there was an open letter published about the EU project where hundreds of investigators have complained about the magnitude of the investment there. So keep your eye on the news for this. It will keep coming. There's also been a lot of news recently about biologically inspired computers. This is recent work done by IBM over the last decade. They just recently announced a brain-like chip with over 4,000 processor cores. These are not Turing von Neumann machines. These are not your ordinary style computers. They are brain-inspired computers. Similarly, my colleague Wabana Boahen, shown on the right-hand side here at Stanford, is engaged in another brain-like computer project with interesting success. Now, what I want to emphasize for the remainder of my talk are some important similarities and some important differences between the kinds of computers we build and the kind of computers we are. And in particular, in what sense are we computers? And what I'd like to do is, by the time I finish, give you a couple of examples of ways in which current neuroscience has led us to conclude that the kind of computers we are fundamentally different than the kinds of computers we've built. And in fact, although it's not part of this talk, a follow-on talk could be focused on exactly how and why combinations of the kinds of computers we are with the kinds of computers we build have the opportunity of being far more powerful than either of those taken alone. I'll leave that as an exercise for the reader.